In the main video, we derived this formula for the acceleration ratio towards two different centers S and S' for any given orbit. We've already seen how this formula helps us derive the inverse square law of gravity if the orbit is elliptical. But what if a particle goes on a hyperbolic orbit? Similar to an ellipse, the defining property of a hyperbola involves the two foci labeled as S' and F respectively. Any point P on the hyperbola has PF minus PS' to be a fixed constant. Another property of the hyperbola involves the tangent at P. The tangent makes the same angle to both segments that connect P to the foci. Once you know these two facts, the arguments proceed similarly to the elliptical case in the main video. First, we need to show that if the force is always directed to S, the midpoint between the two foci, then it follows Hooke's law, except that it is a repulsive force pointing away from the center S. I won't show much detail about the algebra, but basically, you can parameterize the hyperbola as A cos theta, B sin theta, and follow similar arguments in the main video. Now we focus on how we can apply the formula for the acceleration ratio. The first step is remembering how to construct that point A. You construct a line passing through the old center S parallel to PS' to intersect the tangent at A. The whole setup looks a bit different from the elliptical case, but it's the same here. AS is parallel to PS'. And similar to the elliptical case, we want to show that AS is constant. To do that, we first extend the line AS to meet the line PF and call the intersection B. Then we have length AS as the difference between AB and BS. Focusing on this length BS, since S is in the middle of the two foci, we have BS to be half of PS'. In fact, the same setup tells us that PB equals BF. The next step is to rewrite the length AB as something else. To do that, we need to use the property that these two angles are the same. But because PS' and AB are, by construction, parallel, we have a third angle being the same. This implies that AB is equal to PB, so we have AS to be PB minus half PS'. Finally, we already saw that PB is the same as BF, and hence PB is half of PF, and AS is half the difference of the distance from P to the two foci, which we know to be a constant for a hyperbola. The last steps will be identical to the elliptical case in the main video. Just combine the newly established fact that AS is a constant, the acceleration ratio formula, as well as the acceleration away from the center S is proportional to distance. We can also deduce the inverse square law towards a focus of the hyperbola. The case for the parabolic orbit is a bit tricky, but we can cleverly use this acceleration ratio formula to derive the inverse square law. We just need to take the original center S to infinity, so that at any point P, the acceleration points in the same direction, kind of pointing towards a point at infinity. If you parameterize the parabola in a convenient way, then you can see more clearly that the acceleration towards this so-called center at infinity is constant. But how do we compute the rest of the quantities in this formula? We first have to assume that S is at a finite position, just that we need to remember to take the limit to infinity later on. To construct point A, we first draw a tangent at point P, then draw a line from S parallel to PS', which intersects the tangent at A. Now, one important property of the parabola is that these two angles made with the tangent are the same size. That's how parabolic mirrors concentrate the sun's ray onto the focus. Due to AS and PS prime being parallel, there is an extra angle being the same with these two. Then these two angles being the same suggests AS equals PS. But now when we combine these together, we have the acceleration towards S prime to be some constant A times the angular momentum ratio times PS squared over PS prime squared, which doesn't seem right because PS should go all the way to infinity as S goes to infinity, but clearly the acceleration isn't infinite. The trick is to realize that the original angular momentum h also goes to infinity because your center of attraction is infinitely far away. More specifically, h is the magnitude of the cross product sp and velocity v, which is the length sp times the velocity component perpendicular to sp. But here's the thing, the original acceleration always points in this horizontal sp direction, so the vertical component of the velocity is a genuine constant. So combining all these, we really do have the inverse square law. As a summary, if a particle takes a conic section as its orbit, and the center of attraction is at the focus of the conic section, then the force acting on the particle has to obey inverse square law. Again, this doesn't imply the converse. The converse is in any modern textbook on Newtonian gravity. One final point I alluded to in the main video is this. If the particle follows a perfectly circular trajectory, but the center of attraction is on the circumference, then what is the force that gives rise to this? We use this formula again, and we place the original center of attraction S as the center of the circle. If this is the center of attraction, then we have a constant centripetal acceleration A. But at the same time, PS is the radius of the circle and stays constant even when P goes along the orbit. Unlike the parabolic case, we are not taking these s to infinity, so these angular momenta are again constants. All these constants suggest that the acceleration towards any other center of attraction s prime is proportional to as cubed over ps prime squared. Again, we just have to remember how to construct this point A. Draw a tangent at P, then draw a line from S parallel to ps prime to intersect the tangent at A. Now the radius of a circle is always perpendicular to the tangent, so we have a right angle here. By extending the radius to a diameter, we can make another right angle subtended by s prime on the circle. In addition, these two angles are the same because of the parallel lines we drew, and let's call these angles theta. Then there are two ways to write cos theta because of these two right angle triangles. The first way concerns this triangle in a semicircle, and the second way concerns this triangle APS. This relation would imply, after cross multiplication, that AS times PS prime equals PS times BP. But now notice that PS is the radius, something that's constant as the particle traverses this orbit, and BP is the diameter, again constant along the orbit. This allows us to conclude that AS is inversely proportional to PS prime. Finally, we use this inverse proportionality and the formula for the acceleration we previously derived to see that the force or acceleration has to be inversely proportional to the fifth power of the distance. This specific inverse fifth power law has been singled out in Newton's Principia. Anyway, I hope you appreciate how powerful this formula for the acceleration ratio is. I'll see you next time in the main channel video. Bye!